So the speaker for our next plenary talk, it's a pleasure to have James Miller Jones, who's going to tell us, his title is High Resolution Imaging of X-ray Binaries, and he'll also tell us something about how ngEHT can help. Go ahead, James.
Thanks very much. Can you see my screen?
Yes.
Super. All right, well, thanks very much to the organizers for inviting me to give a talk about some of the exciting science that we're already doing with X-ray binaries and how the ngEHT might be able to help. I'm going to talk about, first of all, what are X-ray binaries, how do we study them, give some interesting recent results, particularly relating to dynamical imaging, some examples of some preliminary work that the collaborators listed here have been doing to apply some of the EHT machinery to these X-ray binary systems, and then a little bit at the end about what we might do with the ngEHT and some of the considerations that we'll have to bear in mind. Okay, so X-ray binaries are, in Roger Blandford's words, quasars for the impatient. They're effectively scale models of active galactic nuclei, but with the black holes being so much lower in mass, they evolve much faster. And so they're really good jet launching laboratories. We can see how changes in the accretion flow lead to consequent changes in the jets. These things can evolve on timescales of minutes to hours, as I'm going to show you, which provides a fantastic opportunity to look at the coupling between the accretion and ejection phenomena that we can then hope to scale up to improve our understanding of more massive black holes in active galactic nuclei. So you can see here on the left-hand side a schematic picture of an X-ray binary. We have a black hole or a neutron star accreting from a less evolved donor star. We have an accretion disk and jets being launched from the inner regions. On the right-hand side, you can see a comparison of two different sources, the AGN 3C120 and the X-ray binary GRS 1915 plus 105. And the X-ray binary evolves much more rapidly. We have this time period covers 11 days, and the ejector are traveling 600 milliarc seconds in that time, whereas the AGN jets cover 6 milliarc seconds over 18 months. And this will cause some issues for very high resolution imaging of these fast-moving components. The downside to studying these X-ray binaries is that we have much less resolution in gravitational radii. So in M87, the resolution with the EHT is of course sufficient to image the photon ring and the black hole shadow. So we're getting down to only a few gravitational radii, whereas for a typical image of an X-ray binary jet, this is a system called Cygnus X1, the resolution allows us to get down to maybe 10 to the 7 or 10 to the 8 gravitational radii, just because while they're closer, they are so much lower in mass. However, they do evolve relatively rapidly, as I said, and so provide a complementary view into the physics of accretion and jet launching and the link between them in particular. So when we're looking at these X-ray binary jets, we tend to study them mainly over their outburst period. They spend most of their time typically in a very low luminosity quiescent state. And then during an outburst, they will get bright for a period of a few weeks to months and then fade away again. At the peak of that outburst, the jets start off as relatively steady flows. We call them compact jets. They are not really evolving very quickly in time. They are continuous flows, and they're not nearly as extended as the brighter jets we see later in the outburst. So this is the best example is Cygnus X1 on a size scale of a few milliarc seconds. At the peak of the outburst, the jet morphology changes as the morphology of the accretion flow that's powering it evolves. So the accretion flow goes from a relatively puffed up vertically extended flow in the inner regions to a standard thin disk configuration. And at that point, the steady jet that we've had earlier in the outburst disappears, and we see bright, relativistically moving ejector that can be tracked over the first few days with VLBI, and over many tens or even hundreds of days with connected element interferometers such as the VLA or even ngEHT. So you see on the right-hand side here, images of tracking one of these transient jets with a combination of the VLA and ngEHT imaging. So the aim here to determine the link between accretion and ejection is to look at what's happening in the accretion flow at the point when these jets are actually launched. And that tells us, you know, how do these jets get ejected, what's going on to launch and accelerate them. So on the left-hand side here, you can see some work from Felix Mirabel from a couple of decades ago, where they looked at one of these black hole X-ray binary systems. And the ejection of the jets, shown in green and red here for the radio and infrared bands, is linked to the evolution of the X-ray flow, which is seen in the accretion flow seen in the X-ray bands. So you can see the X-ray light curve in black on the top panel, and then in the lower panel, an X-ray color. And so the jet is thought to be ejected at the big spike around 8.2 hours in this figure, which is just as the X-ray color changes rapidly. So not only does the X-ray spectrum and the X-ray count rate evolve as the jets are ejected, but also the X-ray variability properties. So on the right, you can see some work showing how the types of variability shown with the different symbols in this middle panel evolve as the X-ray color is evolving. And then in the right-hand panel, the stars denote where VLBI showed the jet to be ejected. So we can see that as the type of X-ray variability and the level of X-ray variability change, that is associated with the ejection of jets. In this particular case, that ejection event was only localized to within about half a day, and the accretion flow is evolving much more quickly than that. So what we would really like to do is to be able to accurately track these ejector back to determine a much more precise ejection time, so we could see what it is that's causing the ejection of these jets. Of course, higher frequencies probe closer to the jet base where things are in order to see the optically thin emission. And so with some higher frequencies with the ngEHT, we would be able to get much closer into the jet base. And an example of why this is important is shown in the right-hand figure here from my student Callan Wood. With connected element interferometers, that's the bulk of the points shown here. And this is a time period of a few hundred days. But with VLBI, we were able to get down to just a few milliarc seconds from the core and get a much more precise constraint on when these jets were ejected. I think it was within a window of about 30 minutes. We can determine the jet speeds and the inclination angles, which give us Doppler factors and hence energetics. We can look at how the jets are expanding to get their opening angles. Polarization can give us the magnetic fields. And we can see by tracking these proper motions whether the jets are decelerating and what that tells us about their energetics. Now, the trouble with this rapid evolution is that it is violating a fundamental assumption of aperture synthesis, which is that things remain steady over the course of an observation. So here you see VLBI images of one of these jets in a particular system, and you can see these are daily observations, and you can see the jet is moving significantly over the course of just one day. In a more extreme case, some of Alex Tetarenko's work that's already been shown this week shows that in the millimeter band, the flux densities are evolving on timescales of just minutes. And so that is going to cause issues with trying to make an image over any reasonably extended timescale. So Shep's talked a little bit about trying to make movies of black holes. Well, been making movies of these sorts of jets for a while. Here's a classic example, the processing jet system SS433. Each of these images was made over a course of a few hours, 2 to 3 hours per epoch. So there's not too much smearing over the course of one observation in this case. However, about 6 years ago, there was a very bright Eddington limited outburst of a particular black hole X-ray binary called V404 Cygni. You can see the X-ray light curves down here in the bottom panel, and this was both very, very bright and also very highly variable in the X-ray band. You can see excursions of 3 orders of magnitude or so over just a few minutes. So this was a fairly spectacular and extreme example of one of these events. We think what happened is that as the accretion rate got very, very high, the inner disk was puffed up into this slim disk configuration shown in the top right panel. How we saw that disk affected the X-ray observation. So it was at times partly obscured by the clouds coming off the disk and the slim disk itself. Whereas on other occasions, we would see right down into the inner regions close to the black hole. So in the radio band, this was also very highly variable. So here's the radio light curve over the 2 weeks of the outburst in this bottom panel, and the red and blue bars show our VLBI observations of this event, the X-ray light curve again up at the top. And you see these fairly highly variable jets all the way through the outburst up until about day 10 when things calmed down a little bit. And in VLBI imaging, we could show that these were due to jet ejection events. So I'm going to show movies of 3 of these here. So here's the first one at the beginning of the outburst, and you can see a set of ejections being launched, moving out, and then fading. And we see similar things in every one of these observations that we took early on in the outburst. These jets are evolving very rapidly, and each time bin here is just a few minutes. So jet ejector were continuously being ejected, and one observing strategy in terms of triggering, because this was such a continuous, a long-term event with continuous jet ejections, we would not need to be on target very, very quickly in order to catch these. We had a little bit of time to respond. So I show a set of examples of the jets that we made from this data set. The top row shows 8 gigahertz images and the bottom row shows 15 gigahertz images. So you can see the jet morphology changing over the course of that few days in the top panel. And on the bottom panel, that's from just the blue observation shown here in the middle, which is just over a 4-hour period. And you can see the jet morphology changing rapidly. Not only was the morphology changing, but so was the orientation of the jets, which suggests very rapid precession of the jet axis. So here's a movie of that 4-hour observation in the middle of the outburst that I showed you, so that you can see how this evolves. Every frame is just 2 minutes long, and we binned these data into short snapshots to make sure that neither the morphology nor the flux density was changing too much within any given snapshot. So this is a very, very dynamic system, and we needed some new techniques some modified techniques from the standard procedures in order to figure out what was going on. A standard observation length image would just show a big blur dominated by the central point source. So by analyzing these images, we were able to identify 13 different components, and we tracked their flux density shown on the left panel and their positions on the 2 right panels here. And you can see that each of these jet ejector were moving ballistically upwards, so with a linear motion. And we could identify some components that were moving along similar position angles and ejected at the same time. And we could use that to determine some of the physical properties of the jets. So we take these proper motions, for which the formulae are given in the top right-hand corner there. And then given that the distance to the source is known very well from VLBI parallax, we could then uniquely solve for both the inclination angle and the speed of these jets. So you can see that they are all relatively mildly relativistic. So speeds of 0.3 to 0.5 C or so. The markers in this right-hand figure are where we had corresponding pairs of ejector and could solve uniquely for both speed and inclination angle. Where we didn't have paired ejector, so we only had a single component moving in one direction but no counterpart on the other side, we could only plot these loci of constraints on beta and theta. So this tells us that A, the Lorentz factors were not particularly high in this case, and B, that the position angle and the jet speed were changing significantly over the course of just these 4 hours for different ejector. I mentioned that the jets were precessing over the course of this 4-hour period. So looking at the relative position angles, we could put an upper limit on that rate of precession of just 2.6 hours. It could be as low as 1 second because we could only sample the jets when we saw one of these ejector moving outwards, and we only had a limited number over that 4-hour period. The lower limit is set by the requirement not to process so rapidly that each component is smeared over a large range of position angles. So you can see the precession cone showing up very well as I plot the vectors of each of the components on this right-hand figure. So the best explanation for this precession was that it was actually lens-tearing precession of a misaligned accretion disk. The period of that precession should depend on the black hole spin and its accretion rate. And for the range of periods that we're considering, this implied an accretion rate of about 10 times the Eddington rate, depending on what the spin was. This has been seen in general relativistic magnetohydrodynamic simulations. So this is some work from Matthew Liska from a few years ago with a thick accretion disk and jets that are launched from the inner regions, and you can see that the jets and the disk can precess together. And so the moving jet axis, this precessing jet axis, can tell us something about the precessing in a disk on much smaller scales. So this is very interesting in what it's telling us about what's going on down in the inner regions and the way that it's probing accretion rates and spin from some of the constraints that I showed you on the previous slide. Okay, so I mentioned at the start of the talk that the key thing with these transient jet ejector was to try to couple their launching point with the ongoing changes in the X-rays. We couldn't do that very well in this system V404 Cygni that I showed you because of the obscuration that I mentioned before of the X-rays from the inner part of the disk. A different event, only a couple of years ago, we were able to do this much better, thanks both to some innovative new techniques from my student Callan Wood that I think Rob Fender already showed you
Sorry,
on Monday.
Jay, I think we have a question here.
Okay, sorry, I can't see this in the chat.
From Andrei Lobanov.
I was just booking myself for the end of the talk.
Oh, booking.
Okay. May I carry on?
Yes, sorry.
Okay. So this is the best example to date we have of the link between the jet ejection and the changing X-ray properties. So we have the radio light curves in the top panel, X-ray light curves in the next 3 in different bands, and the X-ray variability properties in the bottom panel. And the ejection date of one of these jets is shown by these magenta bars. And you can see that that tallies very well with both a big change in the soft X-ray light curve and also a change in the variability properties with what we call the quasi-periodic oscillations. So peaks in the X-ray power spectrum rising in frequency and then fading away. So this is due to both very good tracking of the jet proper motions and a new technique to be able to do that, as well as very dense X-ray coverage. Okay, so we want to try and make that even better in future and really get down to what's going on. So some ways forward that we've been exploring recently. So looking to try and jointly fit the light curves, the multi-frequency radio and submillimeter light curves, together with the image morphology to get much better constraints on the jet properties. And this will require synchronization of the VLBI or EHT observing campaigns, as well as with a bunch of lower frequency observations of the jets. In some work with Michael Johnson and Katie Malman and their groups, we've been looking at deploying some of the EHT algorithms that have been developed to get better characterization of the jets and use more of the information, the closure amplitudes and phases as well, to make us more independent of calibration errors. So nested sampling is one thing that we've been looking at. So this is a particular evolving jet from the end of the outburst, and some examples of what the nested sampling is showing for the separation of the two components and their flux densities. So this is just a slight improvement on the diff map model fitting methods that we'd used in the past. Michael's also run some dynamical imaging algorithms on the data. So on the left, I'm going to show you the positions of the model fitted components from our diff map work that from which I showed you the movie earlier, with running dynamical imaging on the same data set. So these two show very, very similar features. And so we're interested in looking to see how we can take data from not just one frame, which is what we did with the diff map modeling, but also taking information from the surrounding frame through some of the regularization to get a better handle on what's going on and have more information when we're reconstructing what's going on. And now the movie just runs backwards. So I'll pause it there and move on. Excuse me. Okay, so what can we do with these jets with the ngEHT? So as I've shown you through this talk, these jets can be very, very rapidly evolving. So we're going to need dynamical imaging techniques to get the most out of the data. Looking at the suite of X-ray binaries that have been studied with VLBI to date, the proper motions range between about a handful, so say 4 and a little over 100 milliarc seconds a day, which means that if they would move across a canonical 25 microarc second beam in somewhere between a few tens of seconds and a few minutes. So we're going to have to be very, very focused on snapshot imaging and any algorithms that can maximize the amount of information that we get out of such images. Another point that I wanted to raise is that rapid response is going to be essential. Jet opening angles are not very well measured, but the constraints are all less than about 5 degrees. There's one recent case where it has been well measured at about 4.5 degrees. So with a range of proper motions above, that would mean that they would be expanding at somewhere between 0.4 and 10 milliarc seconds a day, which, assuming a shortest baseline giving a resolution of something like 200 microarc seconds, means that these ejecta would be resolved out somewhere between a few tens of minutes and a few hours after launch. If the opening angle is a bit smaller, that goes up from a few hours to a few days. So this would dictate the period that we can for which we can follow such ejecta, and also how rapidly we would need to respond to multi-frequency, say X-ray notification of these sorts of events occurring. If we move down in frequency, obviously these demands are somewhat reduced because the beam sizes and the largest angular size probed would both get bigger. Nonetheless, what can we do with looking at these transient jets? We can get the ejection dates with these points much closer to the core, to the black hole itself, than we can get to with gigahertz frequency VLBI. We're able to get much better constraints on when the jets were launched and then tie it back to those X-ray signatures that I showed you earlier. We could also see if there's deceleration occurring in the very inner regions, and could that explain why some proper motions are much, much lower than others. And as Rob mentioned on Monday, we could look at how these jets are expanding over time could tell us something about the collimation profiles of the jets. We could also, with sufficient sensitivity, look at some of the compact jets with the ngEHT. So here is the compact jet from Cygnus X1. We think these are continuous flows, but that could be because we don't have the sensitivity and resolution to pick out multiple moving components here. We don't know very well the Lorentz factors of these compact jets, and that will be a very important thing to measure for their overall energetics and feedback to the surroundings. So by studying these, we can get some information that's so far been very hard to come by. And I also wanted to point out what the resolution is. So here's a 25 microarc second resolution, the red arrows on the right-hand panel. on a illustration of the Cygnus X1 system. So you can see that we've got the companion star as the big bright orange thing and the black hole in the lower left of this panel. And you can see the resolution is just a small fraction of the orbit. So that's getting very exciting, really probing much smaller size scales than we've been able to access before. I also wanted to say that we can combine these studies of the sub-millimeter compact jets, which probe close to the core, with even higher frequency observations from, say, VLT gravity that look at in the infrared band. So looking at the differences between these different frequencies can also tell us quite a bit about the structure of these jets. So I'll just finish up by pointing out that the addition of the ngEHT to the suite of facilities that we use to study these jets can extend our coverage over 7 orders of magnitude in angular scale. So while we'd need only timing techniques can probe scales down to the inner regions of the jets and the accretion flow, we can get to about a few 10 to the 5 Rg with the ngEHT, and that would allow us to track the inner regions of the jets all the way out through the compact jet phase, the transient jets that we see moving out to arc-second scales, and even the jet-blown bubbles that we see as they impact on the surrounding interstellar medium in a few cases. So this is an amazing range of angular scales, and probe the jet over there, almost their entire resolution, right out to where they terminate in the interstellar medium, which is a very exciting prospect and can really help us pin down the energetics. So I think I will leave it there.
Thank you. Thank you for the beautiful talk, James. We have some eager questioners here. Let's start with Andre and Yuri.
Yeah, sorry. Very nice, James. Very interesting results. But on the last slide, if you say that what you get at an ngEHT resolution is 500,000 gravitational radii, we know that the extragalactic jets at these distances, they're typically 20 to 40 times wider than, well, 10 times wider than at the beginning. Would you be worried about resolving this out with the ngEHT beam then?
You mean for the compact jets themselves, or do you mean with the transient jets?
Well, the jets in AGN, they expand, and by the time they reach that distance in gravitational radii, they're typically 10 times wider or more than at the beginning. And if you can take the resolution of the EHT, there might be a danger that you just basically resolve this out.
So I think
for microquasars, of course, yeah.
We don't have a good measurement of the opening angle of the compact jets here. As I say, we do have a measurement of the opening angle of the transient jets, and I gave you the numbers for the point at which they would be resolved out. Now, unless the channel for the compact jets is significantly wider than the channel through which the transient jets move, then this should mean that we're not going to be resolving out if we can pick up the transient jets at a certain point, we should be able to pick up the compact jets as well, because they should be carving out a relatively similar channel. And if they're not, then that's also telling us something very interesting about the relative characteristics of these two different classes.
And I presume this science would require heavy phase referencing capabilities for doing them, right?
Yes, we would need, certainly for the fainter ones, the compact jets. The transient ejector can get up to a few Janskys, as Alex showed. So the phase referencing would potentially be less important for those, the real right at the peak of the outburst. But in the rise phase, where the jets are significantly weaker, maybe tens of millijanskys, then yes, I think that's going to be required.
Great. We're a little bit over, but we'll take one more question from Razia.
Really great talk. I just got a very quick question about the possible correlation between some of the QPOs that you actually point out and some of the radio jets. Actually, for example, by my very quick search, it seems like there's some black hole candidates like 1743, 322, they both have a radio jet plus a millihertz of the QPO. So of course, there are completely different range of the frequency, but if you have a very versatile jet, how could it be that the QPOs, especially those actually lower frequency QPOs, are coming from a little bit variabilities of that jet? Or could there be completely different sources, like what Matthew is actually, normally talk about this kind of like, inner and outer disks that are actually somewhat, taken away from each other?
So the accretion disk is feeding the jets, and in principle, variability in the disk could then flow through into the jet, and that has been the basis of some jet models. Julien Malzac has worked on some of this connection. The other thing I would say is that the processing jets that we see here, there was a tentative detection of I think it was a millihertz type QPO in this system at exactly the same time as we were observing here, which suggests that yes, potentially there is this strong link between the two. But we can certainly explore this more in the Slack channel if you like.
That would be fantastic. But then what you can get out of it if they are very much correlated? What ngEHT can tell us about the possible correlation between the two, if they are going to be observed simultaneously with Chandra or other actually, instruments or whatever?
Well, I mean, ngEHT is telling us what the jets are doing, and we're seeking to try to correlate that with what's going on in the accretion flow from the X-rays. And so, yes, we would very much want to have simultaneity.
Perfect, thank you.
Okay, great. Thank you very much.
Thank you.